Thank you so much for the invitation. I'm very excited for the opportunity to tell you a little bit about our work. And it might be a little bit different than the kind of things that you were used to, but hopefully it's going to be entertaining. Okay, so in general, my group develops computational approaches to study principles of neurocomputation, in particular focusing on those engaged during complex adaptive behavior. And we do so by combining theory and statistical analysis of neurodata. Now, today I'm going to try to tell you a little bit about one way in which we've tried to bridge the two approaches via trained recurrent neural networks. And before I start, I should say that this is, this is work done by an amazing postdoc in my group, David Hocker, in close collaboration with the experimental partner, Cristina Savin, also from NYU. And I'm going to jump straight into the business of the task. So the specific task that we're going to focus on today is a value-based decision-making task that's been developed recently in the lab of Cristina Savin. So the way this works is the following. Briefly, the animal starts a trial by a central poke, after which a tone, 1 out of 5 possible options, communicates to the animal the availability of a reward offer. This could span from 5 microliters to 80 microliters of water. Now, this reward would arrive as a designated port, showed here in yellow, but the time of the reward is uncertain. And this is drawn randomly from an exponential distribution corresponding to a flat hazard rate. So after being made an offer with a particular volume, the animal has 2 options to choose from. It could either stick around and choose to wait until the reward finally arrives, or at any moment in the trial, it could decide that this is not really worth its time, and it can opt out and restart the entire process by poking into the opposite non-rewarded port. Okay? And because the experimentalists are a little bit mean, there's also a small fraction of the trials when the reward never actually arrives, forcing the animal to engage with this opt-out option. Okay. So what this gives us is a rich behavioral readout of what the animal thinks a particular volume of water it's worth. Might sound too complicated, but there's a simple real-world analog that everybody could relate to. Consider the scenario that you're going out for lunch. When you arrive at the restaurant, you find a queue. Do you wait in line or do you try to find another place? Now, this choice might depend on multiple scenarios. First of all, is going to depend on how desperately you want their specific lunch special. So that is the value of this particular offer. But it also depends on what other options are available, what we typically call the opportunity cost. So if you're in our neck of the woods in New York and you have 1 million very good restaurants that are nearby, you could just go around the corner and find an equally good meal. So it's maybe not worth waiting. On the other side, if you're in a place where there aren't that many good alternatives, you might be more willing to join the line. Okay. Moreover, rats don't have access to Google Maps, so they don't have this information explicitly available, and they need to figure out what other options are there based on their past experience in the environment. Okay, so in order to mimic this sort of the changes in the environment that we're seeing in the restaurant example, there is additional structure in the experiment that specifically manipulates the opportunity cost. So we alternate between blocks of trials with different reward options. There's the mixed block trial when all 5 rewards are available, but there are also low or high block trials where only the bottom 3 or the top 3 options are available. And importantly, the 20 milliliters option is available in all contexts, allows us a direct measurement of how much the animal changes its behavior as a function of the statistics of the world. Okay, now the transitions between blocks are random and not communicated directly to the animal. So it has to figure out from trial and error by just experiencing this environment that the world has changed and it needs to change its behavior accordingly. Okay, so this is the task. Before we actually go into what the animals do in this task, we can ask what should be the correct thing to do in this task. We can first ask what should good behavior look like by constructing an idealized scenario of an agent that knows absolutely everything there is to know about the task and asks how would that behave. And we do this using a Markov decision process formalism. And the answer, I'm not going to go through the math in detail, but the answer looks relatively straightforward and intuitive. So first of all, if the reward is better, you should wait longer. So if you're at your favorite restaurant, you're going to join that line more with higher probability. The second important feature is that for exactly the same reward offer, you're going to wait longer if that's the best of a set of bad options than in the case when it's the worst of a set of good options. So the context should manipulate the amount of time you're willing to wait for a particular offer value. Okay, so what this, of course, like the rat doesn't have access to all of this information, so we won't be able to do all of this precisely, but this gives us some insights into what are some qualitative features to look for in the animal behavior. Specifically, we're going to look at this linear reward sensitivity, that is the slope over dependencies between reward and wait time, and the context dependence as the ratio of how much longer I'm willing to wait in a low block versus a high block. Okay, so this was the math. This is one example rat. And it's not too bad. Qualitatively, we see all of the expected features. So we see that they wait longer for bigger rewards. They also change how long they're waiting as a function of the block. Okay, and this is one example rat, but we can take advantage of Christine's high throughput animal training facility to look at the behavior of many hundreds of rats in the context of this task. And here I'm looking at this ratio between wait time between high and low block at 20 milliliters reward. And again, a good behavior here means that you're waiting longer for low block. So the ratio is subunitary, so smaller than 1. And indeed, most of the rats that Christine is training do the right thing. So wait longer for the 20 milliliters reward in the low block. Okay. So I don't have time to talk about this in detail, but we have a pretty good understanding of how they do it. So unlike the oracle, the animals don't have access to trial-by-trial experience, but they need to sort of dynamically evaluate the opportunity cost from trial to trial. And modeling work from Christine's lab, spearheaded by Andrew Ma, a former PhD student in her group, has shown that what they're doing is actually very close to optimal. So they implement a form of online Bayesian inference where they keep track of beliefs about which block they are in and update those trial by trial as a function of as new information comes in. So the good news is that we understand algorithmically what's going on from the perspective of the behavior pretty well. The bad news is that it's not really clear how these complex behavioral signatures could come about from like neural circuit dynamics and computation. So the main challenge here is the multi-scale nature of the task. In particular, like computations need to unfold on 2 different time scales. So on the fast time scale, the animal needs to keep track of what reward am I offered right now, how long have I been waiting, what kind of options, and sort of like based on those 2 things, decide whether it's worth staying longer or abandoning this enterprise. On the slow time constant, it needs to keep up of the history of what kind of rewards were available in order to know what kind of block it's in. Okay, so this multi-time scale nature makes just engineering circuit solutions really difficult. So when we don't know exactly how to make circuits that do particular function, popular strategy in the field is to try to train recurrent neural networks to do the same tasks and then reverse engineer their solution. So it's sort of like a brute force looking in the space of possibilities to find out what kind of circuit solutions work. So in our case, we approached this by just trying to mimic one-to-one in a reinforcement learning agent what the actual rat is doing. So the agent's task is exactly the same. It gets offers, that rewards come with the same delay, and then they have moment by moment the option of waiting or opting out. Okay, there are two important distinctions. One that sort of in the numerics, we have to like define a maximum trial time, so they can't wait indefinitely because that will sort of like mess up with the optimization procedure. And the inter-trial interval period when our rats do quite interesting things is not taken into account. So we don't let them decide when to initiate a new trial. Okay. So this is the task. We sort of like we've been brainwashed into thinking that the machine learning toolkit will have all of the solutions, so they should work, right? It turns out that it's very, very complicated to get this task to train properly. And although I don't have time to go into the details about how we made that work, we have an entire paper just getting this agent to train and behave sensibly on this task. I'm just going to show you briefly the final solution, so the end point of this research endeavor. That is the architecture of the circuit that we end up with. So we're going to have two modules, an OFC, what we call orbital frontal cortex module, and my transition. That's going to be responsible for this low time constant inferring beliefs about which kind of blocks we're in. And a striatal component that is responsible for taking action. So formally, it needs to keep track of values of states and need to compute a policy about what are good actions to take at this moment in time. The rest of the architecture is simple. So both of these get information about what reward is being offered at the beginning of a trial. And for technical reasons, this also knows the history of past actions and rewards so that it can sort of like keep track of the statistics of the environment properly. So this is an architecture reminiscent of the meta-RL version of Jane Wang and collaborators, for anybody who knows about these things in detail. And I'm not going to, okay, so this entire system, so the two recurrent neural network with the LSTM units and all of this inter-area communication is trained by a single objective that first tries to solve the task using a reinforcement learning actor critic loss function, and additionally tries to maintain the ability to do certain basic skills. So the essence of the solution that we had to find is that the network needs to be pre-trained to have particular computational abilities before joining, like learning the task. And that's a reflection of the kind of skills that the animals brings with it to the experiment. And the kind of skills that we're talking about is ability to keep information in memory, count time, integrate sensory information, and represent beliefs. So what you put all of this together, we finally get a solution that actually works. So we get recurrent neural networks behaviors that closely mimics the animal behavior, not only in the qualitative features at the gross level, but also in the details. In particular, there's this big asymmetry between how much change in behavior you get when switching between a mixed and a low block versus when switching between a mixed and a high block. That's normative, so it's there in the MDP optimal solution, and it's also there in the animals and in the recurrent neural networks. The network also mimics moment-by-moment changes in the beliefs about which block the agent thinks it's in, And this is sort of like what you would get from the statistical model of the behavior directly. So what we think the animal might be thinking about the state of the world based on how it's acting in it. Okay. So at the level of the neural activity, the two networks, the two systems are also quite similar. I said that sort of like it's an important feature of the task that we have two different time constants at which computation happens. We can extract directly via statistical estimator fast and slow inferences on the neural activity dynamics. And we can do that in the recurrent RNN. And here we see in the slow dynamics an encoding of both reward and of block offer. So this slow latent is significantly different in different block types. We can also see the dynamics from moment to moment, how new information changes the beliefs after switching from a mixed to either a high or a low block. And at the fast time scale, we can see the encoding of the reward that gets informs how long should I be willing to wait in this particular target given this particular offer. And there's a one-to-one map between what we're seeing in the recurrent neural network and what we're seeing in the actual OFC activity recorded with neuropixels in rats performing the same task. Okay, so we went a long way to finally get to the point of dynamics, which is what I was promising in the title. So what we tried this RNN for in the first place is because we wanted to understand how could the circuit implement this computation. So what we're going to do is going to open the black box of the trained recurrent neural network and look at the dynamics that it's engaging. Okay, so the way we're going to do that is numerically by looking at the kinetic energy of the system, here shown in the first two PCs of activity. And blue marks regions of the space with low kinetic energy, so where the state of the system changes only a little over time. Okay, so this is a self-driven system, so in the absence of inputs. You can also overlay the actual flow fields, which tells us how do the dynamics of the network change as a function of where the network state is at any particular moment in time. And using optimization, we can identify slow features in this dynamics, which I'm going to show here in the black dots and an ellipse. So here what we have is a fixed point, a saddle, and the line attractor. This doesn't show very well in the raw flow field, but you can do a linear approximation of the dynamics around the slow points identified numerically and sort of extract the true dynamical system structure of the process in those regions. Okay, so two things that are interesting here is that this is a structure that we find all the time. So a lot of them across the networks that we've trained, we always find three slow features of the dynamics in the final solution. The other thing that's kind of interesting is if exactly in the same state space, I overlay the readout that tells me what kind of block does this agent think it's in. So this is a region of the space that when I'm here, it means that I'm in a high block, a mixed block, a low block, respectively. Like those correspond, like each of these regions will have a slow feature attached to them. So that we're going to have a slow feature in each of these subsections, which is perhaps not surprising because the difficulty about the slow component is that you need to maintain information in memory for really long times, for the time scale of many trials. So slow dynamics are supposed to help with that. We can also look at how do beliefs change over time. And here is again, it's the same state space with the dashed line marking the transitions between different beliefs. But now the color marks the probability of being in a mixed block as read out from the network. And transitions between the mixed and the low blocks are slow. I don't have any particular example of, ooh, all of a sudden something changed and I know that I'm in a new block, but rather I have to take stock of average rewards that I've been getting recently in order to figure out that, ooh, all of a sudden I'm getting less reward than I used to, so I'm probably in a low block. And you can see the actual changes in the trajectory of the dynamics across several trials as this transition is happening, which sort of like gives us some direct mechanism for the belief updating. Since I'm almost running out of time, I'm gonna just show you a couple more cute dynamical systems things, and then we can go to conclusions. So one feature that's really interesting for us is that this pre-training procedure, so getting the network to know how to do different kind of skills before like trying to learn the task, completely changes the nature of the solution. So here we have a different kind of network that still does the behavior reasonably, but has only been pre-trained on the working memory component without all of the other additional tasks. And here the solution looks qualitatively very different. It's a single fixed point. It's really transient dynamics that drive the entire computation. So this is interesting because it tells us that the task doesn't really constrain the solution fully, so we can have different computational strategies that look almost indistinguishable at the level of behavior. So this gives us a new insight into how we can look across subject variability, because we have like hundreds of rats doing this task. So we actually can look at differences between them in a meaningful way. Finally, this was all in the orbitofrontal cortex module, so the first module. If we're looking at how the policy is being generated, here things are a little bit more complicated because the flow field depends on inputs from the other module. So it's never completely not driven. So that means that the flow fields are different in different conditions, corresponding to beliefs about being in high block, mixed block, or low block. Qualitatively, it's the same thing. So there's a single fixed point, but its relative position with respect to the readout that tells me should I stay or should I go changes as a function of these beliefs. And we can do a projection along this axis and sort of like get direct interpretability. So the probability of waiting as read out across this axis will change not massively, but substantially with the block type. So I'm going to wait longer if I'm in a low block than in a mixed and a high block. The initial conditions, so far, how far off I start with the dynamics relative to this fixed point, will determine exactly how much I'm waiting in this one particular trial as a function of offer type. So those two things together are enough to recapitulate what we're seeing qualitatively at the level of behavior. So at least at the decision-making stage, we feel that we have a reasonably good understanding of how the process works at the circuit level based on this flow field analysis. The last thing that I'll say is that this pre-training procedure really, really matters. So if we're measuring how much the dynamics change over the course of learning. So this is in absolute changes in synaptic strength. And you can do this also in terms of the number of dynamical features that the system exhibits. We're seeing a massive reorganization of the dynamics that makes learning in the task possible. So we're thinking that what's good for sort of like training these very complex tasks is having a rich repertoire of dynamical systems features to begin with, and then sort of tapping into those in that repertoire in order to use the bits that are useful for the complex task that you're trying to train at the end. Okay, so with that, thank you all for your attention. I would say that first of all, latent state inference is really important. If in any sort of dynamic environment, and animals cannot exclusively rely on learned stimulus response association, and they need to form inferences about the world and adapting them as the world changes. Past experience, like the working memory example that I've showed, might actually change the computational strategies that an animal or a trained agent adopt to solve a task. And we think that's kind of an interesting hook into sort of like linking behavior to neural activity. So the other thing immediate consequence is that you might actually start to think more carefully about modeling this kind of features that the animal brings with it to the experiment in the first place. And finally, what in ongoing work, we're trying to take this dynamical systems analysis back to the data by extracting similar kind of flow fields in the recorded neural activity and doing direct comparisons between the two. So with that, I thank you all again for your attention. This is the amazing team that made this possible. Very great trainees, David Hawker, who did most of the RNN, Danilo, who did the data analysis, and very briefly presented bit of NeuroPixel recordings, Shannon connecting the data, and Christine, who's been an amazing collaborator throughout. Thank you all. I saw that there were some questions in the chat, but I couldn't look at them. So.
All right, let's thank Cristina for the very interesting talk. So right now, I don't see any question in the chat, and if you have a question, you can either put in the chat or simply unmute yourself or raise your hand. Maybe I can start with a clarification question.
Mm-hmm.
So Cristina, when you introduced this animal experiments at the beginning, maybe I missed. I mean, how does the rat know what to expect in a particular trial? Is it accompanied by some
so
kind of signal?
the tone tells it what reward is getting in the particular trial.
There's a tone.
So when
I
it
see.
talks at the very beginning, there's a sound. There are 5 different possible frequencies, and if I'm hearing the lowest frequencies is 5 milliliters, etc.
Okay.
Yes.
And
So
these rats
it
are.
knows for sure what reward is going to. Well, not for sure, because the experimentalists are mean and sometimes they lie. But most of the time, the tone communicates exactly the reward that they were going to get in that trial. And yeah, basically the rest they have to like keep track internally. Like nobody tells them what kind of block they're in.
Okay, and is the delay time also related to the tone and the amount of award?
No, so the delay is a completely independent random variable. Yes, it's not related to either the block type or the reward is drawn from exactly the same distribution ID.
So then, data-wise, when the wait time is measured, so it is measured up to the time when the reward is actually given, right?
Yeah, so that's sort of like the time that would be, the wait time is the time between the offer being presented and the reward actually being given. The opt-out times is measured between when the reward is being presented and the animal poked in the opposite port. So
okay.
it's sort of like there's a little bit of a motor period when sort of like it decided that it wants to go, but it needs to actually get there. So it's a little bit higher than what the optimal agent tells you to do.
I see. So the only thing they need to figure out is to realize, okay, now I'm in the high reward block or low reward block or mixed reward block.
Mm-hmm.
Now I get it. I think that makes things much clearer. So do I see any raised hand from the audience or? I do have another question if people don't mind. So later when you're explaining the dynamics of the streamlines on the PC1, PC2 phase plane, so I mean, I guess one part I don't quite understand is that you're saying like one part of the phase plane correspond to the high block, and then one part mixed, one part low. So when this environmental condition is changed, say from high to low, are we expecting that sort of stream field to change, or
Yeah, so the flow field itself does not change because this is the input independent flow field. So this is in the period of the task when the animal or the agent are sitting they've already gotten an offer. They're sitting waiting. They're deciding, should I stay or should I go? So it's in the waiting for reward period. So the flow field is stationary. The initial offer changes where I start off in the state space, and new rewards will move me along that plane, as I was showing for the transition for the mixed and the low block. But it is a complex dynamic of systems, and there are a lot of different moving pieces. So it's not been very easy to make sense of what the transient inputs are doing to the dynamics.
So how would you associate PC1 and PC2 to some kind of realistic component?
So the PCs are defined as this by the embedding space of the actual activity. And so like you can do exactly the same analysis to actual neural activity. Of course, in the animal, we don't have explicitly the mapping between different regions, like different points in that activity space and behavior, but we can try to infer that via the statistical model fit to behavior directly. So that gives us from trial to trial estimated beliefs of what we think the animals were thinking at that particular trial. So that's one way in which you can sort of like make that map one-to-one.
I see. Yeah, that is a very interesting sort of mapping, and it takes a little getting used to.
Yeah, no, while people are sort of like getting more used to try to directly estimate dynamics from the neural activity, I don't like when the task is sufficiently complicated and the linear dynamics are sufficiently involved, making sense of it intuitively is really not that easy in many cases. So hopefully we're going to get that. Like the community is going to get more used to thinking in those terms, and it's going to get easier as we go, but we're not quite there yet.